The theme for this chapter is slicing up problems into infinitesimal elements. We can then add these up by integrating. And so integration is just an accumulation of infinitesimal pieces. The first example of this approach will be finding areas between curves in this section. So, for example, let's look at this. Let's try to find the area of the region bounded between the square root of x and x squared minus 3x, where x ranges from 0 to 2. So the approach is to slice this region up into infinitesimal pieces. We're going to slice this up into vertical slices of infinitesimal width, vertical rectangles if you like. Here's one such vertical rectangle. I'm imagining that we have a vertical rectangle at every value of x here, where these rectangles are extremely thin. I'll say the width is dx, an infinitesimal dx. And so I'm going to compute this area by adding up the areas of these infinitesimal rectangles. So I need to compute the area of such a rectangle. Well, it's exactly its height times its width. Now, its width, I've already said, is dx, but its height I need to compute by looking at this picture here. Now, the y-coordinate of the top of the rectangle here is the square root of x. It's just the formula for this top curve. And the y-coordinate for the bottom of the rectangle is just x squared minus 3x. That's just the formula for the bottom curve. Okay, so its height is the square root of x minus x squared minus 3x, and its width we already said was dx. So if we simplify this, we find that the area of this slice is given by this formula here. And so, to find the total area, we integrate this. Here, under the integral here, what we have is the area of a particular slice, a representative slice. And the limits of integration tell us which slices to add up. We're adding up all the slices from x equals 0 up to x equals 2. So now we can just compute this integral, and that will give us the area. So let's compute this. So we use the power rule, and then we can evaluate. If I plug in 2, 2 to the 3 halves is 2 times the square root of 2. 2 cubed is 8, 2 squared is 4, and so this is what we get. And if we simplify, then we have the area of the shaded region. Okay, let's try this again. Let's look at the area of the region bounded by the graphs of x equals 3 minus y squared and y equals x minus 1. Now I've sketched this region already, and I've labeled the curves, but I've done so by solving for y in terms of x in each case. So I get y equals x minus 1 is this linear piece, but the parabola is not a function of x because it doesn't pass the vertical line test. I had to describe this curve by two different equations. The top half of the parabola is y equals square root of 3 minus x, and the bottom half of the parabola is y equals minus square root of 3 minus x. Now let's split up this piece into vertical slices. The height of the slice will depend on whether the slice is to the left or the right of this intersection point right here at x equals 2. You'll see why in just a minute. Now if x is between -1 and 2 in this range here, then our representative slice can look like this. The top of the slice is bounded by the linear function, and the bottom of the slice is bounded by this bottom half of the parabola. And so the height will be x minus 1, that's the linear piece, minus the bottom, which is minus the square root of 3 minus x. Okay, and we can simplify that to x minus 1 plus the square root of 3 minus x. Okay, next, for the range of x values between 2 and 3, the top of the rectangle is now bounded not by the linear piece, but by the top half of the parabola. That's the square root of 3 minus x. And the bottom of the rectangle is still bounded by the bottom half of the parabola. So for this range of x values, the height is the square root of 3 minus x, that's the top, minus negative square root of 3 minus x, that's the bottom. And if we simplify, that's just 2 times square root of 3 minus x. So we can now add up all of these areas of all these rectangles by integrating. Well, we have to do this in two parts. We can integrate from -1 up to 2 using this height, and then add up the areas of the rectangles from 2 to 3 using this height as follows. The total area is the integral from -1 to 2 using the first height, right? So for all the rectangles to the left of that weird intersection point at x equals 2, the areas of the slice is given by this formula. This is the height, and this is the width, dx. And then for the part of the region to the right of that weird intersection point at x equals 2, the height was given by this formula, and the width was still given by dx. And so this is the integral formula for the area that we're looking for. And so now we can just compute this. We're going to need to make a substitution to take care of this square root of 3 minus x. We let u equals 3 minus x, so du equals negative dx. Then our antiderivative looks like this. Well, the first two terms in this integral we can just go ahead and integrate. And then I'm just rewriting this integral and this integral using our substitution. Notice that I've changed the limits of integration accordingly, so I don't plan to back substitute. Okay, next I evaluate at 2 and at -1 and subtract. And I've also found the antiderivatives for both these two integrals. Okay, next we evaluate for these two and simplify, and this is the area of the shaded region. Now, there is an easier way to do this problem, which I now want to show you. If we don't insist that we use vertical slices, if we allow ourselves to use horizontal slices, then this problem becomes easier. Here I've drawn the same region, but this time I've labeled the curves in terms of y. I've isolated x in terms of y. Now, I can imagine that this region is made up of these horizontal slices, now having infinitesimal width dy, not dx. And their lengths will be found by subtracting the x-coordinate of the right endpoint of the rectangle minus the x-coordinate of the left endpoint. So the height of the slice is dy, and the length of the slice we write in terms of y, the same variable. So the x-coordinate of the right endpoint was given by the formula for the parabola, and that was 3 minus y squared. And the left x-coordinate is given by the linear piece, and that is y plus 1. And now we can simplify that and find that the area of the slice is negative y squared minus y plus 2 dy. And so since y ranges in this case from -2 up to 1, which by the way you would find out by solving this equation here, you set these two curves equal to each other and solve, and that will give you the y coordinates of these two intersection points, and you'll find that that's -2 and 1. Then the area of the region is found by this. We add up the areas of the slices. Remember, this formula here was the area of the slice, and we integrate this from -2 up to 1. And you can see this is an easier integral than the one we just computed. We can just use the power rule and then evaluate and simplify. So to recap, integration is the accumulation of infinitesimal slices. We break up a region into rectangles of infinitesimal width dx if we're using vertical slices, or dy if we're using horizontal slices. And this choice will determine the variable of integration. Next, we express the length of a representative rectangle in terms of the variable of integration. So this is x if you're using vertical slices, and y if you're using horizontal slices. Next, we integrate to add them up. We use the limits of integration to specify the correct range, and you may need to find the intersection points algebraically first. In the next video, we're going to talk about computing volumes using the same approach of adding up infinitesimal slices. For now, go ahead and answer these questions. I'm essentially walking you through the steps of finding the area of a particular region between two curves. So try your hand at that, and I'll see you in the next video.